Just the when you worry about it, it's just like we're doing 20-30 partners. I don't think I know this out there.
Okay, page 7. Okay, so slope fields. Slope fields is a graphical approach to look at the solutions of a differential equation. So far, I mean, for us, if I ever asked you to solve a differential equation, it's always going to be solvable. But we have very restricted setups for solving differential equations. We have to be able to separate the variables. Not every differential equation can be separated easily. And then we also have to have a rule that can apply for our integral or for our differential equation. You know, we have such limited rules available to us and that we're responsible for, that there's a lot of differential equations that we're not able to solve using calculus methods. But what slope fields can do, slope fields can produce a picture of the solution, what the graph could look like, or what the graph looks like, even though algebraically and calculus-wise, we're not able to produce the problem. Now, we're not actually going to have to deal with those types of problems where, oh, I can't solve this differential equation. I got to create a whole slope field to create that solution. It's more of just understanding how to create a slope field and how to interpret a slope field, or how to identify a slope field with a differential equation. But not so much, we're not really getting a full use out of it where, oh, I can't solve this differential equation. I'm going to create this whole slope field what we're responsible for is going to be just a very minimal kind of basic understanding of slope fields. Okay. Slope fields consist of short line segments representing the steepness sketched across a lot of different points. All right. So these line segments are the tangents to a family of solution curves for the differential equation at the various points. The tangents show the direction at which the solution curve will follow. Slope fields are useful in sketching solution curves without having to solve the differential equation algebraically, or even more where the different equations do not have an algebraic solution to it. We can still get a picture of the solution. Okay. There's some important points here, but this will make sense a little bit later. It says use differential equation to find the individual slope segments, creating the slope field. And they use a solution of the differential equation to match the shape of the slope field. Okay. So let's look at example 1 here. Example 1 says sketch the slope field for the differential equation. Now, this is a differential equation. Differential equation is just a slope formula, right? It is just a derivative equation. All right, so I don't want us to get away from that we're just dealing with a derivative equation that we've seen in the past. Right, all it does is it describes the slope of a curve. If you give it enough information, it'll give you a number, and that number will tell you how steep that point is on the graph. So we're going to be sketching the slopes across those points for all these order pairs that are highlighted. Okay. So I'm going to just identify all those order pairs. I'll start at -1, 2. And I'm just listing out my order pairs here that are identified. Okay. So I'm going to start off by working on this order pair, -1, 2, this order pair here. So if I were to insert -1, 2 into the derivative, what slope am I getting? -1 in for x. 5. Okay, so -1 minus 4 is -5. So that's the slope that I want through this point. So you're not going to be graded on accuracy. You can just do ballpark value, whatever you think -5 is, that's good enough. So it's a pretty steep slope. On the AP exam, if you were asked to do a slope field, they're just going to be looking to see, okay, did you graph a negative slope, a slope 0, or positive slope? They're not going to be trying to grade it based off of how steep that graph is in terms of accuracy. They just want to see a positive slope, negative slope, or 0 slope. Okay, what about -1, 1 into the derivative? -3. So we'll make this slightly less steep. -1, 0, and for x and y. -1 minus 0 is -1. So through -1, 0, you're just going to sketch what you think is the -1 slope. Okay. -1, -1. -1 plus 2 is 1. So now we definitely have to change the direction of that slope, right? We're going to make it a +1 slope. Okay. And we're just going down the line here. Plug 1, 2 in. Now, if you're ever asked to create a slope field, the most AP exam problem will ask you this maybe like 8 to 10 points. Okay, but this is very limiting, right? We're not able to really get a picture as to what the graph is doing. There's not enough points here for us to really see. But on the next page, you're going to see a whole slope field filled out with hundreds of points. We're never going to be asked to create anything as large as that. The more important thing is if you're given a completed slope field, you should have to be able to pull necessary information that they ask about that slope field. Okay? So the most you'll create is something small, and you're never asked to interpret what the graph looks like based off of what you drew because there's not enough points. If they're going to ask you about interpretation, they're going to give you a completed slope field to work with.
How did you know the points were -1 and 2? You just made it up, or?
So we're on the AP exam, they will highlight the order pairs that they want you to work on.
Oh, you got it.
Yeah. So you see how there are 8 points highlighted. So on the AP exam, if they gave you 8 points highlighted, they're going to ask you to fill out the order. They won't give you a table like this. I'm just doing the table here to kind of help us see how I'm getting that slope value and where those slope values are coming from. Okay, so see if you guys can try this. I do want to point something out here. What happens if I plug in -1, 0? Undefined. So undefined slope, some of you may interpret that as a vertical tangent line, but on the AP exam, you have to leave it untouched. Okay, leave it blank. If you do anything with it, you're going to get points taken off. Same thing on the test as well. You have to leave. Okay. The biggest mistake that I see is students want to put a vertical line there. So vertical line is considered incorrect. You just have to leave it blank. Okay. I know what you mean if you do a vertical line, but we're looking for an empty point. And then a slope 0 would just be a horizontal line. Slope 0 is horizontal line. Undefined slope is blank. Okay, check your answer when you have finished. Okay, let's go to the next page. Okay, so now this is a slope field that's completely filled out, right? We're having a much easier time kind of visualizing what graph is trying to show us. But you're never going to be asked to create something as large as this. But we will be have to interpret or be able to know either what solution goes with it or what differential equation goes with it. Okay. So one thing that we like to point out is, can we find out some general information? What general slope behavior do we see across the slope field? So if you look at all these slopes here, what's the general consensus here? Most of the slopes are what?
Vertical tangent.
Not vertical tangent. I know this looks almost like vertical. Also, if it is truly a vertical tangent, it shouldn't even show up. All right. So these are all mostly positive slopes, right? Except what? Except at 0. So that's something that we like to look for. Either look for slope 0, positive slopes, negative slopes. Do you see a collection of what general locations do you see positive slopes showing up? Because you're not going to be able to know, okay, this is a slope of 15, and I'm going to plug in this order pair to see if it produces slope 15, right? We're not able to know exactly what that slope value is, but we can make some general observations in terms of, okay, that's a slope 0, that's a positive slope, that's a really steep positive slope, right? That's all we can work off of. But we know that this is true, right? At x equals 0, we're always getting a slope of what? 0. So that means if I were to plug in 0 into the derivative equation, I should always be getting 0, right? So that's something that we can kind of help test. And then also another thing you guys mentioned was most order pairs produce positive slope. So what I like to do is, I'm not really looking for the correct answer initially. I'm just trying to eliminate the wrong answers, right? And then if I'm having to deal with two that I can't differentiate, then I have to maybe look at some specific order pairs and say, okay, at 1, 1, that's a positive slope, plug it in. Okay, can I take out the other one? But the easy thing to do first is let's just eliminate all the ones that we know can't be true, right? So basically, if I plug in any order pair, and if I can imagine getting a negative number in return, that one's out, right? Because there's no negative at all this entire through. So what about A? Can I keep A or remove?
You keep it.
I can remove it, right? Because can you imagine plugging in a number and getting a negative number in return? Yes, right. There's no negative result. So this can't be it. Okay. 3x squared, keep or remove? Keep, right? This is definitely possible because I'm not getting any negatives if I plug in any x value. It's always getting squared. And if I plug in 0, I'm getting 0 as well. So this is a possibility. We're gonna hold on to this one. Okay. 2x plus y. No. Can you imagine this producing a negative value? Yes, right. It's possible that this produces a negative value if if x is both x and y are both negative, or y is more negative than x. So that one's out. How about x over y?
Take it out.
Take out as well. This one, you see that y in the denominator? That means we should be getting something where the entire y-axis is undefined, but we don't see any undefined, right? So there's a possibility for undefined here, but I don't see any empty spaces. So this one's out, right? Natural log of x. This one I can remove, right? Because natural log of -4 doesn't even exist. So if natural log of -4 doesn't even exist, this whole side should be blank, right? It should be completely empty. I'm never able to get a log of a natural log of a negative value. So really, I'm just down to one option, right? So I think that's the strategy for these multiple choice problems: is remove all the wrong ones, and then you're either staring at the correct answer, or you may have to work a little more to decide between two. Okay. All right, now I want to talk about how we can look at this from a different perspective. Okay, let's solve this differential equation. Okay, because the derivative, we can obviously match up the slope value with order pairs, but I want to show you something else here. Let's solve this differential equation. So I'm going to get to a function version of this differential equation. So let's say dy dx equals 3x squared over 1. Okay, let's cross multiply and go through our steps here. 1 dy equals 3x squared dx. Okay, I can put a 1 in front, take the antiderivative. Okay, what's the integral of 1 dy?
Y.
Just y, okay. Y is equal to 3x squared becomes what?
X cubed.
3x cubed over 3 plus what? C. So my equation is x cubed over 3 plus c. Now this is a cubic function, right? That's a cubic
I
function.
don't think it's X cubed over C.
Oh, sorry. It's just x cubed. Remember that. Just x cubed plus c. Yeah. Now that's a cubic function, right? Cubic function looks like this. Right. All right. Do you see that shape showing up? Yes, so we're going to sketch a graph through this point. So we're just going to follow the flow of this graph here. And we can clearly see that cubic function behavior. Okay. Now, notice that plus c also can apply to this one, because imagine this is y equals x cubed plus 3, or y equals x cubed plus 4. If it's a different y-intercept, then it can also handle. It'll have a different starting point, but it has all the different variations of y equals x cubed plus c, with that shift in that c value shifting the graph either up or down depending on what that c value is. So there's two ways that we can match a slope field. If you're at the derivative level, then you're looking at each individual order pair and seeing what the slope behavior is. But if you're looking at from a more macro view, right? If you take a step back and look at the pattern of the slope field, that's going to match the shape of the general equation. Okay. So sometimes you're dealing with a matching problem where they're looking at it from a derivative level. Then you can look at what we did initially. But if they gave you a bunch of general equations, then you have to look at the shape and match the shape with what you know to be true about that equation. Okay, so let's look at next example here, example 3. Okay, can you make some general observations about this slope field? Okay, give me some things that you notice.
And the top quadrants, it's negative. Oh wait, it like
Yeah. What do you notice about the different quadrants?
they all face the origin.
Okay, but in terms of positive slope, negative slope, zero slope, what can you conclude? Quadrant 1 is all what? Quadrant 2, quadrant 3,
Positive.
quadrant 4. So that's a lot of good information, right? That means, oh, any order pair that I plug in first quadrant, I got to get a positive number. Any order pair I plug in from the second quadrant, I got to get a negative number, right? So that could help us eliminate a bunch of things. Now, I do want to point something out here about the y-axis. Sorry, x-axis. This looks like what? This could be interpreted as what?
Undefined.
Or
Zero.
slope zero. So just be careful. Sometimes they're not making it easy on students. They don't. They're either hiding a slope zero or it's showing a slope undefined. So we can't rely on this. Okay, but this we could rely on because this, right? This is actually showing a slope. What? This is empty, right? Because if it weren't, then something should show up. There's no such thing as, well, also if it's a vertical tangent line, it'll be hidden, but that's also slope undefined. But we know this, we can interpret this, right? We can interpret this as slope undefined. So that means at x equals 0, I should be getting undefined slope. But sometimes they are able to hide the y-axis from you because they would have the tick marks and the tick marks, you don't know if you're looking at a tick mark or whether you're looking at the slope. So sometimes they use that to hide as well. So just be careful that sometimes the x and y-axis are not as helpful as you would like it to be, even though because the axis is hiding some information. Okay, so okay, let's look at our options here. Can I keep or eliminate for A?
Eliminate.
Eliminate, right? I can imagine creating, picking an x value and get a negative number, which we know we can't. So this is obviously out. X cubed.
Take it out.
Take it out, right? Because third quadrant, I'm getting a negative positive value, but I can produce something over here that is negative. X minus y.
Take out.
There you go. Y over x.
Keep it.
We can keep, right? And also this matches this nicely, right? That undefined slope divided by x is going to work. E to the y, this we can remove as well. Right, because e raised to anything is positive, right? So everything should be showing positive, but we're not seeing that. Okay. Now, let's solve this different equation so we can kind of see, I want to give you a different look as to how we can match the general equation with the shape of this graph. Cross multiply here. X dy equals y dx. Okay, I want to separate the variables, right? So my dy dx's are in the right places, but what needs to move if I want this to be
X and
separate?
Y.
Yeah, so I need to divide the y over, and I need to do what?
Divide that.
So I'm going to do a double division here. So I'm going to make both the x and y swap places. They're going to both end up in the denominator of your equation, which is okay. As long as your dy dx's are up top, we have a rule for this. Okay. 1 over y dy becomes
Natural log. Absolute value.
Yeah. 1 over x dx becomes, yeah. Okay. We can solve, we can get this out of natural log by raising both sides with e as the base. E to the natural log of y becomes just y. E to the natural log of x becomes, well, let me write this out first. both I can clean up, right? This becomes absolute value of x, this becomes c. So absolute value of y equals absolute value of x times c. Clean all this up, the absolute value can drop out because the c will absorb both. Y equals cx, what is this? What type of equation is this?
Linear.
Linear, right? And you see all these linear graphs here, that makes sense, right? All these positive and negative slopes. The equation matches the shape of this graph.
So you can just remove the absolute value of x.
Because the plus and minus can all be taken in by the c.
Okay.
Okay, let's go to page 11 and let's just try a couple of these. See if we can match the appropriate differential equation with the slope field. So starting on page 11, I'm gonna just start writing down some properties and seeing if I can begin to eliminate some of the wrong choices. So for number one, oh, sorry. For number one, what gives it away is that y-axis. That y-axis is not showing any slope field values. So I know that it must be undefined. So that means when I plug in x equals 0, I must get slope undefined. The only way I can get anything slope undefined is usually with a denominator, right? I don't see any denominator for my first two options, so I can quickly eliminate those two. And then between the last two there's no x in the denominator for that third option, that's removed. And I'm just looking at that fourth option. Another giveaway is that all your slopes are pretty much, I don't see any positive slopes, right? Everything is a negative slope. So the only way to guarantee a negative slope is if every order pair that you get, you force it positive, and then you're only having one negative there, right? So this is always producing a negative value, except when it's on the y-axis. So you want to look for a collection of slope 0, slope undefined, or positive slopes or negative slopes, and use that to help you eliminate wrong choices, okay? Rather than looking for the right answer. I like to look for the wrong answers first to make it a little faster. Okay. There's a nice property here. What do all these look like? More specifically, this looks like slope 1. So it looks like whenever my x and y values are the same, I'm getting a slope 1. Right? That's a nice property to identify. And then most of your slopes is showing what? Positive, right? So that means we can eliminate all the ones that shows negative. Right, no negative slopes. This one's out, this one's out. So when x and y are the same value, I'm getting a slope 1, so it looks like this is the best fit, right? Okay, let's just do two more, and then I want to talk about verifying solutions using differential equations. It's not hard. It's just kind of have to get used to those types of the way they word those problems. Okay, number 3. Nice. Something very useful about this is what? Not horizontal asymptote, but a slope 0 when what? Yeah. So that should help us out. Also, something I noticed is anything that is in the first quadrant, when y is greater than 2, I'm getting positive slope. When y is less than 2, I'm getting negative slope. All right, so we can use that to maybe eliminate some of the wrong answers. Here, if I were to plug in 2 and for y, I'm getting undefined. I don't see any undefined here, right? So no, this one is not correct. Here, if I plug in 2, 6 or 3, 8, I'm getting, this is telling me I'm getting a negative, but all I see is positive here. So this one I know is incorrect because it's x squared is always positive, y minus 2 squared is always positive. So that negative in front is going to force this to always be negative, but I see some positive slopes here that is conflicting with this one here. Okay, let's try one more here, number 4.
I remember earlier you said like it looked like a linear line positive, but like can't I say this looks like a circle, like there's some circular shape.
So another way you could do it, we could solve this differential equation and see if that turns into a circle shape. But I think it's faster to just eliminate the wrong choices, right? Right. Yeah, because if you were to match that circle shape, you have to solve the differential equation first before you can see that connection. Here, if I plug in order pair 2, 3, I'm getting a positive result, but this is negative, so I know this one's out.
Why is B out?
Oh, why is this one out?
Yeah.
Because if I plugged in 1 for y, I should be getting undefined. If I plug in 1, I'm not necessarily getting undefined. I'm getting 0, which is that's not seeing that. In here, we just have to kind of play around with different order pairs in different quadrants until we can decide which one we can remove. And it's gonna have to be that first one we can remove. This one. This one's the best fit.
You have to show, but do I have to show my work?
No, there's no work shown. You just have to like the right answer. Okay, 10 minutes here. Let me have us try these verifying equations here. Okay, so it says the function y equals e to the 3x minus 5x plus 7 is the solution to which of the following differential equation? They all involve y prime and y double prime. So what we're going to do is we're going to find y prime, y double prime, and then we're going to test them out to see which of these will produce an equation that works. So we're going to only be able to do this if we have the derivatives in front of us. So let's just find y prime and y double prime and see if we can begin to narrow down our options. Okay, what's the root of e to the 3x? Yeah, e to the u times u prime. Okay, easy enough. Y double prime is what? Good.
3x.
Times 3, yeah. So there's a e to the u times u prime. Another 3 shows up that merges with the 3 coefficient here. So it's just 9e to the 3x. Okay, so we're just testing our answer choices through substitution to find a match with the original equation. Okay, so it's a little bit of trial and error here and see if I were to insert these in, which one will produce me a 0. So here, I'm looking at option D here. If I plugged in 9 minus 3, there's no way that these can cancel out. So I got to find a way where the 3 and 9 can cancel out. C is not going to do it for me either. It's either A or B. Which one will get me there? Close. A will get us there. B is not, that plus 15 is not going to quite get us to where we want. So it's going to be A, right? So if I replace y double prime with 9e to 3x minus 3 parentheses 3e to 3x minus 5, clean that up. This will give me a positive 15 minus 15. That will give me to a 0. So yeah, between A and B, it's going to be A. Right. It's not hard. We're just having to kind of get used to the way that they present these problems. Okay, everybody good with one? Yeah, so basically you just have to find your derivatives and see which one fits. Okay. Okay, number 2 is a little bit different here. A curve has a slope 2x plus 3. So this is actually another way of saying that's my derivative. Okay, dy dx is 2x plus 3. Which of the following is an equation of the curve that passes through? So why don't we just solve this differential equation? A plus c will show up, plug in the order pair to that to find that c value, and then we have our equation. So cross multiply here. Okay. Plug in my order pair 1, 2. Right, 24 is a little bit tedious. We have to find each of the derivatives and then see which one can fit into the solution set. But it's a good chance for us to practice all of our derivative rules. Oops. Negative 18 minus 60 plus 9. There's no way that can get me to 0, right? So we know that this one's out. This one we can keep. Third one we can also keep. Okay, we begin quiz review on Monday. I'm almost, I have the review worksheets for one review worksheet that we can begin on Monday. You can choose, you can feel free to pick it up now or pick it up Monday. But if you want to get a head start, just looking at it, you can pick one up. I'm almost finished with the key. I'm gonna put the key for the quiz review on the website later this afternoon. So we'll start review Monday. If you want to start, take a look at it, you can pick one up. All right, come pick your phone. Yes, the package should be uploaded. If not, I'll do that now.
I mean, it makes sense. Let's just, oh, wow. What we're gonna be into is, what we're gonna be into is,
I know.